Welcome again to my class on fundamentals of electrical engineering. We are discussing the fundamentals of signals and systems in module 4. I hope we all remember that any system can be described using a pair of signals essentially, and the nature of the signals add to the classification of the systems. So we start with continuous time systems, and then we'll move on to discrete time systems. We normally will be holding on to linear time invariant systems or linear and time invariant systems. Since nonlinear systems are a class by themselves, you can't use most of the analysis tools that we have for linear systems. Okay? And time invariant systems also help us to use most of the very interesting tools for solving analysis, etc. Okay. So, and then, of course, all engineering as also real systems are causal in nature, and engineering systems need to be stable, because only then we'll be able to control the system, as also try to get something or the other from the system. So, in fact, all real systems will be stable because nothing goes to infinity, because that is generally the definition of having an unstable system. But at the same time, in the zone of operation, the stability is very, very important. So in that context, it's a little different. Okay. So we used Laplace transforms as the elementary tool for representing the system as a model, and the first model is the impulse response. We also have other models in the using Laplace transforms. Okay, so the Laplace transforms are normally used for dynamic systems because constant coefficient differential equations can be again used to model the systems. Okay, so we move on to. We were discussing the Laplace transforms as tools for analysis, as also a solution of continuous time systems. Okay, and of course linear time invariant systems, because we do not right now move on to nonlinear systems and time varying systems. Okay, so let's look at some of the questions that could not be covered in the first session. In this session, again, we are discussing Laplace transforms, and let me hope that we go a little deeper, a little broader. Okay, so let's look at the first question. The Laplace transform of t square minus 2t ut minus 1. So first and foremost, you catch on to ut minus 1, which means that this signal, okay, the Laplace transform of a particular signal is asked, or function is asked. This function or signal starts only at t minus 1. So it has validity only if the function is expressed in terms of t minus 1. So t square minus 2t needs to be expressed as t minus 1 whole square. So what do we have when we have t minus 1 whole square? It is t square plus 1 minus 2t. So only t square and minus 2t are given. So you add a 1 as also remove a 1. So we have t minus 1 whole square ut. So function ft, okay, whatever is given is re-explained as t minus 1 whole square ut minus 1. The one that we added, now we deduct with ut minus 1. So now you can take its Laplace inverse. So what emerges from t minus 1 ut minus 1 whole square t minus 1 whole square ut minus 1 is the same as the Laplace inverse of t square when it is delayed by a time unit. So that's equal to 1 by s 2 by s cube, and you also have e raised to minus s to explain the fact that this particular part of the signal, this is only part of the signal, is delayed by 1 time unit. What about the other part? Other part is minus 1. That will give you 1 by s as the Laplace transform, and then it is delayed by 1 time unit, or you multiply this term by e raised to minus s. So the answer is going to be 2 by s cube e raised to minus s minus 1 by s e raised to minus s. Okay, so the fourth option, or D option, or C option. Okay, sorry, the third option or C option. Okay, so let's go to the second problem. A rectangular current pulse of duration t. How do you explain a rectangular pulse? By saying that that you have two unit step inputs. one starts at t equal to 0 and another one of course deducts from it, so you have ut and ut minus t, capital T. Okay, so that explains the rectangular function. It's a pulse, you can also call it as a pulse. Okay, and so what's this Laplace transform? You have 1 by s rectangular pulse of duration t and magnitude 1. Okay, so x rectangular can be easily explained as equal to ut minus capital T. Okay, as the Laplace transform what? Okay, so the first term gets 1 by s, the second term gets again 1 by s but delayed by capital T, so e raised to minus ts. Okay, so the fourth option, 1 by s into 1 minus e raised to minus ts or exponential minus ts, happens to be the correct option for selection and marking as your option. Okay, so let's go to the third question. Which of the following statements is true about the two-sided Laplace transform? So we have taken we start the integration of the Laplace transform of a function ft. So how do you find the Laplace transform? Ft into e raised to minus st dt. You integrate it from minus infinity to plus infinity when you are looking at a two-sided Laplace transform. Okay, so what are the different statements given? The first statement is it exists for every signal that may or may not have a Fourier transform. This is not true. It may not exist for, okay, the Fourier transform and Laplace transform need not have anything to do with each other. Okay, so that option is disregarded. It has no poles for any bounded signal that is non-zero only inside a finite time. Okay, so the statement is given in a convoluted manner. So I would say that it has no poles for any non-zero, any bounded non-zero signal which is applicable for a finite time interval. In this case, we see that for a finite time, the region of convergence happens to be the entire S-plane because of the two-sided Laplace transform. So we see that it cannot have any poles in this context. Okay, so the option B is right. Okay, the number of finite poles and finite zeros must be equal. This need not be true for all cases. Okay, so if a signal can be expressed as a weighted sum of shifted one-sided exponentials, then its Laplace transform will have no poles. This is also not true. Okay, so option B is correct. Okay, let's move to the fourth question. The output response of a system is denoted as yt and its Laplace transform is given by ys is equal to 10 by s into s square plus s plus 100 root 2. Okay, the steady state value. So what do you mean by steady state value of yt? Y infinity, or you can obtain it by multiplying ys by s and then setting s as equal to 0 because it's the steady state of y infinity that is required. Okay? So s and s cancel, and then when you set all s as equal to 0, numerator has 10 left, denominator has 100 root 2. On the other hand, if the initial value needs to be found out, again you multiply by s and then you take out all the s because now you've got to set s is equal to infinity. So you need to cancel out all s. Okay, so that such questions are not asked, but please remember. Okay. So, okay, so now we have 10 divided by 100 root 2 or 10. Okay, so we have 1 by 10 root 2 or option A as the correct answer. Okay, so now we go to the fifth problem. What does it tell us? A system transfer function is Hs, which has a numerator as given by, or ns. We call it as a numerator polynomial in S. A1 s square plus b1s plus c1, and the denominator polynomial ds is given by a2 s square plus b2 s plus c2. Okay, so if a1 and b1 are equal to 0, so numerator is very simple now. It's just a constant divided by a2 s square plus b2 s plus c2. Okay, and all other coefficients are positive. The transfer function represents what? Okay, different types of filters are given. So how do you do that? Okay, so you can so first and foremost you set s as equal to j omega, and then you set omega is equal to 0, and or you set at the other end when omega is equal to infinity. Okay, so first on the numerator we have c1, and when you set s as equal to j omega, you see that s square a2 is equal to that is denominator is minus a2 omega square plus b2 j omega plus c1. Okay, in this when you set omega is equal to 0, you see that the whole thing, the whole transfer function boils down to C1 by C2, which is a good value. That is, when omega equal to 0, it means that at very low frequencies, it has a particular transfer function, or in other words, it is conveying some message to the output. Okay. On the other hand, if you set omega is equal to infinity, then the whole thing collapses. You see that it has only a 0 value, or in other words, there is nothing given to the output, or in other words, it's a low pass filter because it works at omega equal to 0. Okay. Yeah, so so that's all. That's how you find out what is the kind of filter. Okay, so you can on the other hand, if at omega equal to infinity you have a particular value, this happens when you are having an s square on the numerator. Okay, on the other hand, if you have s on the numerator, then it becomes a band pass filter. Okay, so let's go to the sixth problem. The inverse Laplace transform of hs equal to s plus 3 divided by s square plus 2s plus 1. This is a very interesting problem in the sense that first and foremost, the denominator must be seen as equal to s plus 1 whole square. Okay, so that's the first stage. Second is, the numerator must be seen as s plus 1 plus 2, okay, such that we have s plus 1 by s plus 1 whole square as one term. That will give you 1 by s plus 1. That will give you the first e raised to minus t as its Laplace inverse. Okay, and then you have 2 divided by s plus 1 whole square. So 2 divided by s plus 1 whole square will give you 2t e raised to minus t. Okay, so in a very simple manner, by splitting up both the numerator and the denominator into components, wherein we are having the factors of s plus 1 whole square in the denominator and s plus 1 plus 2 on the numerator. You can easily find the Laplace inverse of such a given quantity. Okay, so now let's go to the last problem in this session, wherein the relationship is given the relationship between the input ut and the output yt to be yt is equal to 0 to t. Okay, it looks like a convolution. 2 plus t minus tau e raised to minus 3 t minus tau u tau d tau. Okay, so here it's better. So the transfer function y is by us is asked. Okay, so the best option that I suggest is to put t minus tau is equal to theta. Okay, so we see that now we have 2 plus theta and e raised to minus 3 theta. U tau becomes so u tau becomes minus d tau. Okay, so it becomes u tau becomes u. You have t minus theta, and d tau becomes the same as equal to minus d tau. Okay, so we see that now the limits also change. The limits can be now transferred. So you see that finally you have gt, okay, as 2 plus t e raised to minus 3t. Okay, and so gs. So now it's easy to, and it is finding the Laplace transform. So you just find out gs as equal to 2 by s plus 3 plus t. T will give you t e raised to minus 3t will give you 1 by s plus 3 whole square. Okay, so now combine them together as having 2 into s plus 3 divided by s plus 3 whole square plus 1 by s plus 3 whole square is the same as equal to 2s plus 7. Okay, so the trick here is to substitute for t minus tau as equal to theta, such that you are having d tau would be minus dt, minus d theta. Okay, so and the limits will be changing in terms of by substituting for tau as equal to 0. You see that you will have the lower limit as equal to theta is equal to t, and the upper limit will be when you substitute for tau as equal to t, the upper limit will be 0. So when you the minus value can be compensated using using the negative sign. Okay, so this is one way of doing the problem in a simpler manner. I hope this is well understood, as also whatever we discussed with respect to a filter, with respect to final value theorem, which was already covered, with respect to the fact that a two-sided Laplace transform will have no poles for any bounded non-zero signal, where it is non-zero within a finite time interval. We also realize that if a signal starts at t equal to tau or ut minus tau. In that case, we have to convert the entire signal pattern such that it can be expressed in terms of t minus tau, or t has to be replaced by t minus tau in the consideration. Okay, so with this, I hope that whatever has been covered in the 2 sessions of Laplace transform is well accepted by you and well understood, as also very useful for you. Thank you.